Okay, so what I want to do today is to continue our discussion on support vector machine. Now, last time we talked about the basic formulation of support vector machine. I drew you some diagram, introduced this concept of margin, and then I tried to convince you that by maximizing the margin, I'm going to get a classifier. This classifier is not the same as the Bayesian classifier. It has a different objective, which is to maximize the margin. Now, what I want to do today is to talk about the dual perspective of the support vector machine. Last time when we talked about support vector machine, we also tried to introduce the optimization formulation. And that formulation, if we want to call it, is called the primal version, primal support vector machine. And then what we are going to look at today will be called the dual support vector machine. Now, we need to go into the dual space for several reasons. The first reason is that in the dual space, you will be able to see why this thing is called the support vectors. Okay? Why is it called support vectors? Because in the dual space, you can show exactly that the solution will be defined by a few vectors. And these are called support vectors. The other reason why we want to go to the dual space is to introduce a thing called a kernel support vector machine, kernel SVM. And in the kernel SVM, we are able to put in nonlinearity. As what we have done before, when we introduced linear regression, we also talk about this kernel trick. So the same kernel trick can be applied to the SVM, but it can only be applied in the dual space and not the primal space. The primal space is a lot harder. Okay? All right. So here's the agenda. The agenda has two parts, to talk about Lagrange duality and then talk about the dual SVM. Okay, so to start with, let me remind you what is a support vector machine problem. Now, I don't want to go back to the beginning of support vector machine by defining the max, margin, that kind of thing. I would just call like the textbooks. This is the support vector machine problem. We're trying to minimize the magnitude of this W, subject to the constraint that all these training samples, they are correctly classified. Okay? Now, just remember that the meaning of this constraint is that this is the predicted label, and then this is the true label, and then the multiplication of the two has to be positive. And this one comes from the fact that we are normalizing the space, and so this one will reflect to the smallest margin that we were discussing. Okay, so this is a good SVM. This is because the margin is maximized, and then the data points, they are living on the correct position. Okay, now this is not a very good margin because the margin is not maximized. So this is not a solution. So I want to introduce this concept called the dual SVM. But before I do that, of course, I need to tell you what do I mean by dual optimization. And so let's look at this problem. This problem, it is a constraint minimization problem. Okay? And in addition, this is a inequality constraint optimization. Now, you can describe it as hard. Okay? It is a difficult problem. Now, how are you going to solve this problem? Well, you are going to define something called the Lagrangian function, and the Lagrangian function will contain two terms. One comes from the objective function, this term, and then the other one will comes from the constraint. Okay, so this is the constraint, and there's something called the Lagrange multiplier, lambda j, and you need to sum them over all the possible j's. Okay, so this is called the Lagrange multiplier. This is called the objective function. And then you sum them all. This is called the Lagrangian function. And then, if you want to solve for a solution for this problem, then the classical optimization says that you need to find a saddle point of the Lagrangian function. And by saddle point, I mean that you take the gradient with respect to your primal variables. Okay, so this is called the primal variable because these are the variables that you want to solve originally. You take the gradient of the Lagrangian with respect to these variables, you will get 0. In addition, if you take the gradient of the Lagrangian with respect to your Lagrange multiplier, you will also get 0. Okay, so now you need to solve this pair of equations in order to get the solution for this primal problem. Is that okay? All right. Okay, so now I want to jump a little bit to the appendix to make sure that everyone is on the same page as me. Okay, so now if you go to the appendix of the lecture slide, you can see that I pretty much just grab over the tutorial to here. So if you go to our course website, go to the tutorial number 4 will contain this material. Okay, so what is this appendix? Well, this appendix gives you a quick review of how do we solve a very generic constraint optimization. Okay, something that we sort of touched on that, but it was not very in detail. Okay, so if you have an inequality constraint optimization, the very, very general form will be given by this. You have objective function, and then you have constraints, and then you have an equality constraint. You have a set of constraints. And then the classic optimization literature will say that, look, you need to form something called the Lagrangian function, like what we are doing. Okay, form the Lagrangian function for the inequality constraint, and you have a Lagrangian for the equality constraint. So you form this thing called the Lagrangian function that involves both inequality and equality constraint. And then the Lagrange multipliers, as I'm saying here, these are also called the dual variables. Okay, it's just a name that goes with the Lagrange multipliers. So how do you know that your estimate, it is a true solution to this optimization problem? Now, there is a list of 4 conditions that you need to check. And these 4 conditions, they are called the KKT conditions. And it's very, very standard conditions that you need to check. The KKT conditions, they are the first order conditions that does not provide any second order information. So if you're looking for the second order information, then the KKT condition is not sufficient. Now, in this KKT condition, what do we need? Now, we need to have these 4. The first one is called the stationarity, meaning that if you take the gradient with respect to your primal variable, it has to be 0. Right? That makes a lot of sense because you want to find a stationary point for your original problem. And so by taking the gradient, it has to go to minimum value. Okay, so that has to give you 0 in terms of gradient. Okay, so primal variable should be stationary. And then the second criteria is that when you put your x star, which is your solution, into your constraint, of course they have to be satisfied, otherwise you are violating the constraints. So this is called the primal feasibility. The third constraint is that it's called the dual feasibility, which if you go back a little bit to the equation here, you do have a assumption that these mu's, they are positive. Okay? If you don't have that, then the Lagrangian won't be abound below. So you want to make sure that the mu's, they are positive. That's called the dual feasibility. There's no constraint for the equality constraint. Okay, so if you recall in many lectures ago when we talk about the equality constraint, there is no such kind of thing on the equality constraint dual variables. Okay, but for the inequality, we do need to have this criteria. The last one is called the complementary slackness. It says that the product of your Lagrange multiplier and also your inequality constraint has to be 0. So if one is 0, okay, if one is positive, then the other one has to be 0. Okay, that means if your solution x star can make this inequality constraint to be inactive, meaning that it's strictly greater than, then your mu has to be 0. Vice versa, if this is equal to 0, then this guy can be a positive number. Okay, so these are the 4 conditions. Now, I'm not going into the detail of these constraint optimization, and I just want to point out that if you read the appendix, I have an example here that shows you for problems like these. This is an example. Let's say you have a minimization with an equality constraint, and then you have an inequality constraint. How are you going to apply the KKT condition to solve the problem without resorting to things like CVX? Now, of course, you can solve the problem using CVX, but can we get some analytic solutions? And that can be done by just analyzing the KKT conditions. Okay, so I'm not going into details of this example. I encourage you to take a look. Okay, so they are very, very good examples showing you how you can leverage those. So let's go back to our main subject, which is to talk about the support vector machine. Okay, all right. So we're here. So let's look at the support vector machine problem again. And in this problem, what we have, well, this is the Lagrangian function. We have the objective function, and then we have the constraint. The constraint here is 1 minus the product of the label and prediction, and so it has to be non-positive, okay? Because one is always bigger than the other. Now, this is negative, and then this is always positive. And now you can look at the complementarity condition. What it says is that if your lambda j is positive, and then this one has to be 0. And then the other possibility is that lambda j is 0, and then the other one is negative. This is what the complementarity condition coming out of the KKT condition requires you to satisfy. Okay? So you must have this pair of criteria. And so if you want to make sure that if you take the gradient of this guy, okay, so if you take the gradient with respect to lambda, okay, because to solve this problem, you want to take the gradient with respect to the primal and also the dual. If you take the gradient with respect to lambda, you make it to 0, then what will happen? Well, if you take gradient of L with respect to lambda, what is the gradient of this? That will become 0. Why? Because it doesn't contain lambda. Okay. How about the other guy? The other guy would just be the gradient of this summation. Well, I'm not evaluating this, right? But you can see that it will be the gradient of this quantity. Okay. And then and so if you want to make this to 0, then effectively what you're asking is that you're asking this quantity to go to 0, this gradient to go to 0. And if you want to ask this gradient to go to 0, what are you asking? Literally what you're asking? Well, you're asking this thing to go to either max or mean, because at max or at mean, you will get 0 gradient. Okay? Now, you won't get a saddle point because this function is linear in lambda. So you either can go up or go down. You will never get saddle point. Okay? So if this is going to maximum or minimum, now let's look at this quantity. Which case will it be true? Whether it's a maximum or minimum. Well, this number is what? This number is negative. Okay? And this number is positive. Okay? And so no matter what lambda you choose, this will always go down. Right? It's unbounded below. You can never reach a minimum point. And so this one has to go to maximum if you want the gradient to be 0. Do you guys follow me? Okay? Because you want to find the gradient to be 0, and it's impossible to get a minimum because the product of these two terms is always negative. It's unbounded below, so you have to reach a maximum point. And therefore, by taking the gradient with respect to lambda, making the 0, you're finding a maximum point in the dual space, okay, of the dual variable. So what? Well, so if you look at the optimization problem, then there will be you can partition the problem into 2 steps. The first step is really trying to say, look, what would be the maximizer of my constraint equation? Okay, so what I'm going to do is that I'm going to define lambda star as the guy that can maximize my constraint. Okay, I'm just maximizing the constraint part in my Lagrangian function. I need to maximize because of the argument I just gave you. You cannot minimize, and you want the gradient to be 0. Okay, it has to be maximized. So now you have this maximization going on, and then let's say that I have already found this lambda star, and I want to plug in to your Lagrangian function. And then that would be a function in just w and w0 in terms of the primal variable. And now you also want to take the gradient of the primal variable, make it to 0. And in this case, of course, you want to have a minimum point. And so what you're doing is that you want to take the gradient of this L, set it into 0. And so you want to minimize this. And now if I replace this lambda star by this quantity here, okay, so meaning that in the Lagrangian function, instead of just writing this, I'm going to write the maximum of this by finding a good lambda. Right? So you see that originally you want to solve this minimization problem, and then there will be a lambda star. Now I'm replacing the lambda star by the lambda star that maximizes this quantity, and therefore this quantity has to be maximized. Once you maximize this quantity, then you see that the problem will become this. This is the same as here. So in this equation, I'm saying that, okay, well, I want to maximize the overall Lagrangian because this W has nothing to do with your lambda, so you can move the maximum out of that, right? So now this problem becomes what? You are minimizing over W and W is 0. Inner loop will be maximized over the lambda. So this is a mini-max problem, okay? Mini-max problem. It is a very, very typical problem in convex optimization that you want to minimize in one direction, but then you want to maximize in another direction. Okay? Now, we're not going into details of this mini-max problem because mini-max problem will take another week in a convex optimization course to discuss, and another 2 weeks to discuss all these Lagrange dualities and so on, strong dualities and things like that. So we are not going into the details. However, I want to point out that if you want to solve this original problem, essentially what you will end up having is to solve a mini-max problem. Okay, and this mini-max problem is not easy to solve. Okay, and when you plug into a CVX program, what they're doing, they're actually solving this problem for you magically. Okay, you don't know what's going on, but they're solving this problem for you magically. So there's a very, very important thing about this minimax problem, and it's stated by a fact called the strong duality. The strong duality says that minimax will equal to max min. Okay? Now this equality is not always true. It's true when you are solving a convex optimization. You are solving a strongly convex optimization problem. Okay? Now, in our case, we have a fairly simple problem. It is a quadratic minimization subject to linear constraint. And this is called ECE in the convex literature. And strong duality will hold for this quadratic programming problem. And therefore, min-max will become the same as max-min. Now, you ask, so what? Well, I'm telling you that mini-max is hard. Max-min could be a little bit easier. Now, I'm not saying it is a lot easier. It's just a little bit easier. Now, this a little bit easier will show up when we talk about the kernel method. Okay? All right. So we are going to turn this primal problem, the original problem, which we know the formulation, which we dump it into CVX. We are getting solution. Now we're turning it into a max-min problem, which you can also dump it into CVX. It will also give you a solution, but we will be able to write down the form a little bit more clearer so that we can apply those kernel tricks. Now, this figure here shows you what do you need to have this strong duality. Strong duality says that the primal objective function and then the dual objective function, that there's a gap here. That gap is called the duality gap. That will be 0 if your strong duality holds. Okay, so this is some technical details that you need to learn when you go to a convex optimization course, and I'm skipping the details here. Okay, what I want you to realize is that for the problem that we are considering, primal equals to dual, minimax equals to max-min. Okay, so that's the message here. So let's look at a toy problem. Okay, just to gain a little bit more insight. Let's say you want to solve this primal problem with what? With certain variables. Okay. Now this primal problem can be written as this form of minimize this u square subject to a j transpose u bigger than bj. Right? So I can literally rewrite this original problem into this format, and then I can define a two-dimensional problem in this example. and then I can choose all the AJs, and then the BJs, and so on, and then put it into this constraint. And we ask, okay, can we write down the dual problem for this optimization problem? And it turns out that yes, we can write it down fairly easily. So you can write down the Lagrangian function of that problem, and then you have two constraints, the first constraint, the second constraint, and then you take the minimization over the u, so you take the gradient with respect to u, setting to 0, then you can the u's in terms of the lambda 1 and lambda 2 and lambda 3, and then you plug into this problem. Okay, so the plug into this Lagrangian function, then you get everything in terms of the lambdas. Isn't it interesting, right? Because originally you were solving this problem, and then the Lagrangian would be everything expressed in terms of your primal variable and also the dual variable. Okay, and in this example, the Lagrangian function is written in terms of u and the lambdas. And then after I calculate the gradient with respect to u's, I'm just substituting all these u's into the equation here. And then the u's will be gone. The thing that will be surviving will be the lambdas. And then you are getting a problem in terms of the lambdas. Okay? And then you have a constraint because you're looking at a inequality constraint problem, so you have lambda bigger than 0. This is what? This is called the dual problem. Okay, so this is called the dual problem. And by solving this dual problem, you will be able to find a good lambda. And by finding a good lambda, plugging here, you'll be able to find the primal solution. Okay, so now I'm not declaring that by taking this approach, you have an easier problem. The problem is as hard as before. However, this gives you a mechanism to solve the problem. This is called a dual problem. And so what you are going to see is that the support vector machine problem that I'm describing can be written into this form. Everything can be described in terms of the lambda. And then after I solve for the lambdas, I will be able to find out the solution of the primal variables. That means I will be able to solve my support vector machine problem. Okay, so have we gained anything? Well, here's the dual problem, right? So you have all these terms surrounding here. And then all these terms they are negative. Okay, so these terms, they are negative. And so we must have lambda 2 equals to lambda 3 equals to 0. Now this is only true for this example. Okay. Now why do you want why can you set that to 0? Well, because this term, this and these four terms, they are always negative, because the lambdas, they are always positive. Okay? And so if you don't choose them to 0, then it will become unbounded below, and then you don't have a solution. And therefore, you have already chosen the lambda 2 and lambda 3 to 0. Then this problem can be simplified to this, and then this problem is fairly straightforward. It's just a quadratic equation in one variable. Take the gradient set to 0, get lambda 1 equals to 4 over 5. Then you can find out the u1 and u2 by just substituting the lambda 1, lambda 2, and lambda 3. Now, not all problems are as simple as this. Okay? This is just one very special case that you can get these solutions. Okay? Now, what we are going to do in the support vector machine case is that we are going to write down the dual problem, and then we are going to substitute into the primal problem and see if we can get some solution. Okay? All right.